Hello. Hello and welcome to this video. In this video, we will start with linked list as we have discussed. So we have covered vectors and important traits, and now we will cover linked list. So what I'm planning is that vector we have done linked list, and then we will look at hash map and followed by set or B-tree map and hash map. So these are the important data structures which we have, and we will cover in that order. So we are looking at STD collections linked list and the structure linked list. So this will be relatively shorter data structure because it does not have as many methods as you can see or trait implementations as vectors, but it's still quite useful data structure. It won't be used as much as vectors, but we need to understand that how this works so that for it is useful in certain situations, not always, okay, because linked lists are not O1 time for retrieval of nodes, but vectors give O1 retrieval. So people almost always use vectors in practice. On rare occasions, you will need linked list. So we'll see how this works. So let's start with the reading the documentation and then we'll see the methods. So linked list is a doubly linked list with own nodes. The linked list allows pushing and popping elements at either end in constant time. That means we can use it as a stack or queue or deck because it supports pushing and popping at both ends. A linked list with the known list of items can be initialized from an array. So we can say linked list from 1 to 3. This is an array, and you can create a linked list. Note it is almost always better to use vec or vec deck because array-based containers are generally faster, more memory efficient, and make better use of CPU cache. So we have implementations now. So the new function creates an empty linked list. You create it like this. So you have to specify the type of items in linked list. For example, here it is on sign 32, and the variable name will be list, and the container is linked list. The first function really is append, moves all elements from other to the end of linked list. So it will operate on self, mutable self, and others should also be a mutable linked list. Okay. This reuses all the nodes from other and moves them to self. After this operation, other becomes empty. So other should be also mutable linked list as indicated in the signature. This operation should compute in O1 time and O1 memory. So here we create a new linked list and we push A and we create another linked list 2. List 2 in which we have two elements, list 1 and B and C. And then we call list1 dot append and %mut list 2. And then we create an iterator on the list 1 and we call next, which gives us ABC, and finally we will receive none and list will be empty after consuming the iterator. Then we have new underscoring nightly API, we don't care about it. Then we have iter, provides a forward iterator. So this we already saw, we have a linked list of U32 here. We push 0, 1, 2 and we get iterator, and when we call next on this, it will return an option enum of sum with reference of 0, 1 and 2, and finally it will return none. Note that this iterator will modify the list, okay, because as you can see that it is mutable iterator. The reason why it is mutable and it consumes the items in the list is because if you iterate over all the elements in the list, it will be problematic. Okay. I might be wrong. Let me think. It is not necessary to consume the elements. It can maintain its state. So it is not necessary to consume the elements. Okay, but over here, if you see, yeah, it is not consuming it. List 2 is empty. List 1 is not empty. Okay. It might not consume the list. No, I don't think it will consume the list. Iterator won't consume the list. Then we have iter underscore mut provides a forward iterator with mutable references. So we create a linked list of type U32, we push back 0, 1, and 2, and for each element we get an iterator on iter.mut, and for every element we add 10. So our items becomes 10, 11, and 12. Then we have all the nightly API, then we have isEmpty. It returns true if the linked list is empty. This operation should compute in one time. So we create a variable DL of linked list type, and we assert DL is empty. Then we push func foo, and DL is not empty anymore. Then we have len, which returns the length of the linked list. This operation should compute in one time. That means the list contains the length in the structure. Otherwise, it won't be possible to compute it in one time because it will have to traverse the linked list. So since it returns in one time, we know that it maintains the length, and it does not go through the list counting all the elements. So when you insert elements, push front or push back, when you do, it updates the length. So for example, you push front 2 and length will be 1, push front 1 and length will become 2, and on pushing more, length will become 3. Then we have clear, removes all elements from the linked list. This operation should compute in one time. So you push front 2, push front 1, and length will be 2, front would be sum ampersand 1, and dl.clear will make the length 0, and front will become none. Then we have contains, which should be of the same type of the list, and the trait which we need to be satisfied is partial equality. Returns, this will be required for comparison for contains. Returns true if the linked list contains an element equal to the given value. This operation should compute linearly in n time. So for example, we create the similar U32 list, we push back 0, 1, and 2, and we check whether it contains 0, which should return true, and we check whether it contains 10, which returns false. Note that it takes the reference because the elements can be of quite large size. So it does not move or does not do copying or cloning. It takes a reference for efficiency. Then we have front, provides a reference to the front element or none if the list is empty. This is like the head pointer of linked list. This operation computes in one time. So we create a new linked list. DL.front would be none. We push front 1. DL front becomes sum ampersand 1. Then we have front underscore mut, which operates on the self and returns some mutable reference. Provides a mutable reference to the front element or none if the list is empty. This operation should complete in one time. So we create a DL front and we push front 1, so the head becomes 1. And when we do the front.mut, it might return none, we do nothing, and if it returns something, we assign it the value of 5. So now the front would be 5. Then we have back similar to front, but it operates on the end list or end of the list. Then we have backmut, so similar to frontmut, but it operates on the end of the list. Okay, similar example. Then we have push front, adds an element to the front of the list. This operation should compute in one time. So we have already seen several times. We push front 2, and the front dot unwrap, if you do, it becomes ampersand 2. And we push front 1, and then if you do DL front, we get 1. Then we have push front mut, adds an element to the front of list, returning a reference to it. This operation should complete in one time. So the reference which is returned is mutable, and so we can add plus, we can modify it. So front now becomes 6. It was 2, and we are in 4, so it becomes 6. Then we have pop front. It is like push front, but it returns from the end of the list and returns none if the list is empty. And then we have push back, so pop front, right? And then we have push back. So we don't have a version of pop front mut because the element is given, so we can do whatever we want to do with it. Then we have push back, adds an element to the back of the list. This operation should compute in one time. So you push back, and then if you look at the back operation, it will return 3 here. Similarly, we have push back mut. So adds an element to the back of list, returning a reference to it. This operation should compute in O1 time. So what it returns is mutable, so you can modify it. We push back 2 and we add 4, so the back element would be 6 now. Then we have pop back, removes the last element of the list and returns it, or none if it is empty. Completes in O1 time. So pop back, if you do initially on the empty list created, it would return none. And if you do pushback 1 and 3 and then pop back, then it would return 3. Then we have split off function which takes at argument which is of types usize and returns a linked list of type T and A, where A should satisfy the cloning trait. It splits the list into 2 at the given index, returns everything after the given index including the index. This operation should compute in own time. Panics if at greater than length. So we have a linked list, we push to 1 to 3 at front and we split at index 2. So now the pop front, if we pop front of split, it would be 1. And if we do pop front again, we will have none. So the list would be 3, 2, 1, and you split off at index 2, so 1 will be in another list, okay? Remove, we are not concerned with nightly API. Let me see how much we have, quite a bit. So we can finish this extractive. This is the last function. And we generally won't discuss traits in detail. We have extractive, operates on self, and we have filterF and returns extractive type. And that F should be is a closure of FN type. Mutable closure is there. Creates an iterator which uses a closure to determine if an element should be removed. If the closure returns true, the element is removed from the list and yielded. If the closure returns false or panics, the element remains in the list and will not be yielded. If the return extractive is not exhausted, example because it is dropped without iterating or the iteration short circuits, then the remaining elements will be retained. Use extractive dot for each drop if you do not need the return iterator. The iterator also lets you mutate the value of each element in the closure regardless of whether you choose to keep or remove it. Splitting a list into even and odd values using the original list, that is the example. So we have a linked list of type U32 and we extend it with the reference 1, 2, 3, 4, 5, 6, 8, 9, 11, 13, 14 and 15. And we extract the number if it is even. You see here we dereference the captured variable and we test whether the remainder 1 divided by 2 is 0. We collect it into a linked list and that is our evens and remaining would be odds. Now we transform this into a iterator and collect into a vector, and this vector should be 2, 4, 6, 8, 14 and this should be 1, 3, 5, 9, 11, 13 and 15. So we split into odds and evens. So these were the functions of linked list. Now we see what traits it implements. It implements clone, debug, default, drop. Extend is also a trait which we just saw. Okay. Then we have from iterator hash slice into iterator is there. So there are quite a few iterators it implements. So please go through this list and there are other traits, ref, unwind, self, pin and pin we have not discussed yet, and borrow, not borrow, any, those are also implemented for this. So with this we come to the end of this discussion of linked list. It is quite useful data structure as you can see simply because you can implement stacks and queues using the linked list. Okay, and that is the reason you don't see stack here. Okay, if you try to find stack, you won't get. If you see queue, you won't find queue. Okay, so stacks and queues, if you want to implement, then you should use linked list. Okay, and that makes the data structure very useful. So in the next video, let's discuss which one would we do. We will compute hash map. Okay, we'll do hash map in the next video. So let's see, we go to collections and we look at hash map quite big. Okay, so it might take 2 3 videos to complete this, not as large as vector, but still much larger than linked list. So we will study hash map into the next video, and we'll see how we can use hash maps in our code by following the examples given in the standard library. So I hope that you have enjoyed this video and you got something to learn. So thanks a lot for watching the video. We will meet again after 4 days with the video on HashMap. Till then, stay curious, keep learning, and most importantly, enjoy.